Today we are going to look an example of a rigid body, and we are going to find the matrix of the inertia tensor associated to this example. We are going to start with a cylinder with mass m. In this case, the cylinder will be our rigid body. Okay, and we are going to locate the coordinate system in the center of the cylinder, like this. We are going to use the same notation that we have been using to notate the coordinate system that is primed. So for example, this will be the x1 prime axis, this one will be the x2 prime axis, and this the x3 prime axis. As you can see, we can identify easily that this corresponds to the x, this to the y, and this to the z coordinate. Okay, so again, the properties of this cylinder are going to be that the mass is going to be equal to m. Okay, the height is going to be equal to h, and the radius of the cylinder is going to be equal to a. Okay, perfect. So as we saw on a previous video, we showed that we can find the inertia tensor of a rigid body with the next equation. Okay, this is the equation that allows us to calculate the inertia tensor of a rigid body that is made of a continuous distribution of matter. In this case, it is important to mention that this cylinder is homogeneous. So that means that the density of mass is going to be a constant, okay, and it can be easily calculated just dividing the mass by the volume. So that means that the density is going to be equal to m over pi a squared h. Remember that this is the volume of a cylinder, okay? Perfect. So we are going to start by calculating the components of the inertia tensor. So for example, let's start with the component I1 prime 1 prime. What will that be? Well, we are going to have that this is going to be equal to the density times the integral of this integral is evaluated on a volume. Of course, this b represents the volume of the cylinder. So we are going to integrate this quantity in all the volume of the cylinder. That is an important aspect. So this integral is going to be on this volume, and the Kronecker delta, of course, is going to be equal to 1 because we have the same indices here. So this will multiply the magnitude of the vector r, which is of course x1 squared plus x2 squared plus x3 squared. And then we need to subtract minus x1 prime, because in this case I is equal to j. So this is minus x1 prime, and then all these times a volume differential. Okay, perfect. As I mentioned, this is going to be equal to 1. So we can see that this x1 squared will be cancelled with this x1 squared. Okay, in this case, I forgot to put the prime notation here, but it's not that important. So this x1 will cancel with this quantity over here. So we are going to get an integral like this. The density times the volume integral of x2 squared plus x3 squared times volume differential. Perfect. So looking that we are working on a cylinder, it can be very easy to suspect that we need to use cylinder coordinates. So that means that, for example, the x1 prime coordinate is going to be equal to r cosine of phi, x2 prime is equal to r sine of phi, and x3 prime is equal to z. These are the very famous formulas for transformations to cylindrical coordinates. So that is what we are going to use here. And of course, the limits of integration of this integral of volume will depend on these cylindrical variables that we are going to introduce. the r, the phi, and the z coordinate. Perfect. So what are we going to get? This is going to be equal to the density and the triple integral of, well, x2 squared, but that is going to be, well, r sine squared of phi plus z squared times dv. But you know that the differential of volume in a cylindrical coordinates, well, it's just r dr d phi dz. Okay, so we have r dr d phi dz here, and looking that r represents the radius, well, we know that the radius of the cylinder goes from 0 to a. Okay, so that means that the limit of integration here is going to be from 0 to a. Then we know that phi, well, represents the angle of the vector. In this case, for example, let's say that the vector is located in this point. Well, this phi represents this angle over here. Okay, so we know that to be able to contemplate all the diameter of the cylinder, we need to establish phi from 0 to 2 pi. Okay, so this goes from 0 to 2 pi. And of course, dz, well, is the differential that represents the height of the cylinder. So that means that it goes from minus h over 2 to h over 2. Okay, because remember, well, we are locating the coordinate system at the half of the cylinder. So from here we have h over 2, and from here we have h over 2. Perfect. Okay, so well, we need to calculate this integral over here. Okay, so to solve this integral, well, we are going to start by the differential phi. Okay, so we know that we can express this as the density, the integral from minus h over 2 to h over 2 of dz, then the integral from 0 to a of dr, and then the integral from 0 to 2 pi of, well, r squared sine squared of phi plus z squared d phi. Okay, well, we can spread these r into these two quantities to get that this is going to be r cubed and these r z squared, like this. Okay, so for the variable phi, well, these r's are going to be constant. This is also a constant. So let me split this integral like this. This will be the integral from 0 to 2 pi of, well, r cubed sine squared of phi d phi plus r z squared, the integral from 0 to 2 pi of d phi. Perfect. And we know that there is a famous formula for the sine squared of phi, which is that this is equal to 1/2 1 minus cosine of 2 phi. Okay, so that is what we are going to use. And well, this will be equal to the integral from 0 to 2 pi of r cubed, and then 1/2 1 minus cosine of 2 phi d phi plus, and in this case, this integral is easy to see that this is equal to 2 pi. So we are going to get 2 pi r z squared here. Perfect. You can see that we can split the integral into two pieces here and then for here. So this is going to be equal to r squared over 2 times 2 pi for the integral that corresponds to this one over here. And then minus r cubed over 2, the integral from 0 to 2 pi of cosine of 2 phi d phi plus 2 pi r z squared. Okay, perfect. So we are going to get that this is r cubed over, well, just actually pi r cubed, right? So this is minus r cubed over 2, and then we are going to divide by 2, So we will get a 4 here to get the sine of 2 pi from 0 to 2 pi plus 2 pi r z squared. Okay, and it's easy to notice that if we evaluate 2 pi over here and 0 over here, this whole expression is going to be equal to 0. So the final result of the piece of integral is going to be equal to pi r cubed plus 2 pi r z squared. Remember that this result corresponds to this integral that I'm pointing here. Okay, so let me substitute the result. We are going to get that the component I11 is going to be equal to the density times the integral from minus h over 2 to h over 2 dz, the integral from 0 to a dr, and then times pi r cubed plus 2 pi r z squared. Okay, perfect. So we are going to switch these two integrals. We are going to integrate first the z variable, and then we are going to leave at last the dr variable. So that means that we are going to get here the density times the integral from 0 to a dr, the integral from minus h over 2 to h over 2, dz times pi r cubed plus 2 pi r z squared. Okay, so, well, this is a very easy integral. You can notice that if we integrate this part, looking that it has no z, well, we will get the z variable, and then evaluated in these limits, we are just going to get the total height of the cylinder. So that means that this is going to be equal to the density, the integral from 0 to a dr, and then times pi r cubed h, and then plus, let me split this like this, 2 pi r, the integral from minus h over 2 to h over 2, dz z squared, like this. Okay, so if we keep working on this, we are going to get the density, the integral from 0 to a dr, and then pi r cubed h plus 2 pi r, and here we are going to get z cubed over 3 from minus h over 2 to h over 2. Okay, so we can see this as the density, the integral from 0 to a dr, pi r cubed h plus 2 pi r divided by 3, and then h cubed over 8 minus, actually it will be plus due to the minus of the fundamental theorem of calculus. We are going to get here plus h cubed over 8 again, like this. So this is going to be equal to the density times the integral from 0 to a dr pi r cubed h plus, we will have here, well, 2 divided by 12, which is going to be 1 over 6 pi r h cubed. Okay, perfect. So let me write this in another page. Okay, this is what we got on the integral for the component 1,1 of the inertia tensor. Okay, so we need to keep integrating. So this will be equal to the density times the integral from 0 to I. Well, let me make the integral. This will be the density pi times h r to the 4th divided by 4 from 0 to a, and then plus the density divided by 6 times pi h cubed, and then r squared divided by 2 from 0 to a. Okay, perfect. So it's easy to evaluate in this case, looking that the inferior limit of integration is equal to 0. This will gives us the density pi h a to the fourth divided by 4 plus the density pi h cubed a squared divided by 12. Okay, and remember that we defined that the density is equal to the mass divided by pi a squared over h. So if we use this formula into the result that we got, this pi will be cancelled, this h will be cancelled, we will have an a squared here in the numerator, so we will get ma squared divided by 4, and then plus, again this pi will be cancelled, this a squared will be cancelled, and we will get an h in the numerator times the mass, so this will be mh divided by 12. Actually, h squared, right? Okay, perfect. So this will be the I11 component of the inertia tensor. Okay, well, the other components of the tensor will be very similar to be found. So I'm interested in showing you what happens with the components that are not symmetric, like this one. For example, the component I22 and the component I33, well, they can be calculated on the same way. But, for example, there's a curious thing that happens with the non-symmetric components. Let's calculate, for example, the I12 component. What is this going to be? Well, this will be the density times the integral on a volume of the Kronecker delta I12 prime times r squared minus x1 prime, x2 prime, and on a volume integral. Perfect. So as you can see, looking at this Kronecker delta has different indices, well, it will be equal to 0. And here we are going to get that this is, well, r cosine of phi, and this is going to be r sine of phi. So we will get r squared cosine of phi times sine of phi. So again, the integration of the phi variable is going to be from 0 to 2 pi. So that means that all this expression will have an integral like this. The integral from 0 to 2 pi of sine of phi cosine of phi. So we can immediately see that this is going to be equal to 0. Okay, perfect. And why is this? Well, looking that we are integrating, in this case, an odd function times an even function, so that will give us an odd function, okay? And I know that this is not a symmetric interval, but we can just move the graph of the function to establish some new interval of integration that is symmetric. And again, well, you can see this as that you are integrating an odd function on a complete period of a periodic function, which is the odd function. So that means that the integral is going to be equal to 0 because we are integrating an odd function. Perfect. So that means that the component I12 is going to be equal to 0. What happens then with the component, for example, I23, like this? Well, we are going to get that this is the density, the integral, again, the Kronecker delta 23 r squared minus x2 x3 dv. Again, this Kronecker delta is equal to 0. So we get that here we are going to have r sine of phi, and this is going to be z. Perfect. Okay, so looking that the limits of integration for z are from minus h over 2 to h over 2, that means that we are going to get an integral from this whole integral that splits on 3 integrals. One of those 3 integrals is going to be of the form z dz from minus h over 2 to h over 2. Again, this is an odd function, so it is symmetric on this interval. It's easy to graph. You know that the graph of a function like this is just a straight line. So we are integrating from minus h over 2 to h over 2. That means that, well, the area under the curve here is going to be negative and this positive, so that means that they cancel each other. So again, this is going to be equal to 0. Perfect. And it's easy to see that for the component I1 3 prime, well, it's going to happen the same exact thing. The only thing that is going to change is that instead of a sine, we are going to get a cosine, but that doesn't affect this integral that we have here. So again, the components of the inertia tensor that are not symmetric are going to be equal to 0. Okay, so let me write over here what are going to be the values of the other components that we didn't calculate, just to establish what is the matrix of the inertia tensor. So actually for the I2 prime term, well, we are going to have exactly the same as in the beginning. So this will be equal to m over 4a squared plus mh squared divided by 12. Okay? And for the I3 term, if you make all the process exactly the same, well, you will get that this is going to be equal to ma squared divided by 2. Okay, so this will be the final component. So what is going to be the matrix that represents the inertia tensor? Well, we are going to have that ij is going to be equal to, and let me take out a common factor of m divided by 12 to get that this is going to be equal to 3a squared plus h squared. This term is going to be the same, 3a squared plus h squared. And this one is going to be 6a squared. And of course, the other components are going to be equal to 0. Perfect. So this will be the final result of the video. The important thing, that is the matrix that represents the tensor, the inertia tensor of the homogeneous cylinder.